today my presentation is mostly going to be focused on fiber-reinforced plastics, since I think that's applicable to a lot of the people here in the area. And before I get started, I just want to acknowledge our partner in this presentation, which was Solvay's Engineering Plastics Division. So we have a really nice collaboration with them where we're basically doing a lot of a long-term fatigue and durability study project that involves a lot of material testing, a lot of analysis, and kind of really pushing the boundaries in this world. So Solvay Engineering Plastics, they are a material supplier. They do a lot of work in with like nylons reinforced with glass fibers, as well as some advanced polymers. They're a global company with their center in France. And then over here on the other side, you have the group I represent, which is e-Xstream Engineering. We're an MSc software company. We do both software as well as engineering services. The main product we make is called Digimat, as you guys have heard a little bit already. And we're headquartered in Belgium in Europe, but we have offices all over the world, including here in Michigan. So when you combine the two of us together, what you end up with is basically the Digimat software being used by Solvay as part of their MMI design. And together we have a really nice relationship. We also have relationships with a lot of the other material suppliers, but this is kind of a special relationship around fatigue. So I know that Jeff covered a little bit of the background earlier on these composite materials, but I'm just going to kind of walk through it again quickly just to make sure we're all on the same page here. So when we talk about, if we start with just stiffness to kind of lay the groundwork for all of this, if we talk about metals, traditionally we're talking about one single stress strain curve. Obviously there's a lot of other influences that can come in there, but if we start with the most basic approach. But when we look at composite materials, all of a sudden we're dealing with this heterogeneous material. So we've got both fibers as well as a plastic matrix, and we're going to end up seeing some anisotropic effects due to that heterogeneity. So what we'll see is that even if we start with a really basic plate, part like this flat plate, when we injection mold that flat plate, we'll end up with a fiber orientation that's based on how that part's manufactured. So, in a rough way, you can say the fiber orientations align themselves in the direction of flow. If we then were to take that flat plate and we were to test the stiffness and the strength of it in two different directions, we could do that by cutting out dumbbells in these different directions. We'd see something that looks like this. So basically, you see this very nonlinear stress-strain curve. You see something that's very soft and very ductile when the fibers are not aligned in the direction of loading, and then something that's very stiff and very brittle when the fibers are aligned in the direction of loading. And that's really the anisotropy showing itself. And this is true for both stiffness as well as failure. So you see these different strains of failure as well as fatigue. And so the whole point of all this is that these materials are highly dependent on the manufacturing process. And here I'm really talking about fiber-reinforced plastics, but the same could be said for any composite material that's anisotropic in nature, so continuous fiber composites as well. So the way that we deal with that is we start by looking at the material at a level deeper than at the kind of homogeneous composite level. So we start with the material model that has a description of the matrix by itself, the fibers by itself, a description of what that fiber orientation is, how long are they, how many fibers are there, and then we can then take all that information and homogenize it together to predict what the composite response is going to be. And so the point of this whole thing is that we can have one material model where for any load and any fiber orientation, we can predict what the stress-strain response is going to be and what the strength of the material is going to be. So stiffness, failure, we can handle temperature dependence because obviously these plastics are very temperature dependent, as they alluded to earlier, but the glass fibers are not so temperature dependent. We can look at strain rate dependence because you have the same kind of thing happening there between the plastic and the glass fibers, and we can look at fatigue. So if we talk about, we talked about it kind of at the base material level, but then how does that interaction happen at the part level? And this is the way that it happens. So in a traditional setup right now where you're not taking into account this manufacturing process, you do some work to get some stress-strain curves. You use that to build a material card in your finite element model, and then you can use that to predict your stiffness and strength. And then, downstream do your fatigue calculations. And down here in another group, or maybe at your material supplier, you've got some manufacturing simulation happening. And they're doing that to look at, how can I make this part most quickly? How do I reduce warpage and things like that? And so basically what we do with Digimat is we allow you to take these fiber orientation predictions that are happening down here. So what direction are the fibers facing and how much randomness is there? We can bring that along with this Digimat material and couple that into your finite element analysis so that you can get a very accurate prediction of how the material responds from both a stiffness as well as a strength standpoint, and eventually move on to fatigue. So a quick demonstration of that application. So this is a engine mount problem here. This was Trailborg Vibroacoustics, and they had this steel engine mount bracket, and they wanted to replace it with a nylon reinforced with glass fibers to try and reduce the weight on this part and reduce the cost. And so after they did that, they went through a set of validation tests, as we often do in the industry. And this is just one example of a validation test looking at basically stiffness and strength. And so what they did is they took their part, they loaded it transversely, and then they compared a couple of different analysis approaches with their experimental data. So what you see over here is a force versus displacement graph. You've got the isotropic curve in green up here. So this is kind of taking the numbers directly from a data sheet for this material and plugging into your model. And then in blue, you've got your experimental data, and in red, you've got the Digimat. And you can see that using Digimat with your finite element analysis gave them a pretty much perfect description of the stiffness of the part. Similarly, they were able to get a really accurate description of, where and when they should expect to see failure in this part, as you can see indicated by this failure indicator shown here, and then the actual failure happening inside the part. And doing this transition from metal to plastics gave them a 40% reduction in mass, a 15% reduction in their cost, and this is a part that's actually in production today in Europe and being used on vehicles right now. So we've talked a little bit about the concepts of fiber-reinforced plastics and how they affect the engineering properties of those materials, that heterogeneity affects it. Let's talk about how that then affects the fatigue of the material and how we deal with that. So in a traditional fatigue analysis, you have a couple of different steps, and certainly I would say most everybody in this room is more of an expert on this process than I am, but I'll talk through it in kind of at the level where I see it. So in the first step, we need to determine what our stress field is, because that stress field is what's really going to drive the durability or the fatigue life of our part. So if we look at predicting the stress field of these materials, one differentiation we see right away is that we know we're going to have different stress strain curves at different points. So we're not going to have this uniform stiffness happening across our part, and we're going to need to take that into account. From there, we can then simplify our 3D history into an equivalent 1D history using a stress combination method. We can then do our rain flow counting. And all that's going to happen very similar to what the methodology you guys are used to. And then we need to look at, okay, now that we've actually got our load, how do we figure out what the strength of that is? And then we see our second difference here, which is where we're going to have these different SN curves happening at different points, really driven by that, once again, material heterogeneity. So the takeaway from all this is that our local stress and our damage in our model must change with respect to both our local fiber orientation as well as the load that's being applied to that part. So the way that we're going to handle that inside of Digimat is we're going to use a couple of different damage models. And we have two different damage models that we have developed. The first one is a phenomenological-based macroscopic failure indicator. And the second one is a micromechanical based on damage accumulation in the matrix. So the first one here is really relevant to fiber-reinforced plastics, and I'll talk about it more here in a second. And the second one is really more relevant to unidirectional composites. And kind of the big difference between here is that if you look at a small point in a unidirectional composite, you have kind of fibers running through that point of the material, and all of your fatigue damage, or generally your fatigue damage, is happening inside of that matrix material. So this model is really formulated on the matrix, whereas this model is really focused more at the composite level. So since the topic of conversation today is around fiber-reinforced plastics, we'll look at this phenomenological model and talk a little bit more what it is. So this model is really aimed at tackling high cycle fatigue. So this is, we mentioned before that these materials are highly nonlinear, but in this case, we're only going to be looking at the linear properties here. And this is a strength-based fatigue life prediction. So instead of actually accumulating damage in the material, we're going to go ahead and reduce the strength of the material for each individual cycle that this material is seeing, which is, I think, not so dissimilar from most of the methods we've been talking about today. In order to determine that strength of the material, though, we're going to use what is considered to be a relatively unique approach to the Digimat world. So basically, we're going to use a failure indicator that was developed for unidirectional composites, and you can see it down here. And we're going to apply it in a way that makes sense for a short fiber-reinforced plastic. And the way that you can think about this is we're going to take this failure indicator, that includes the directionality of the material. You can see it's got these 3 different strength parameters here. And we're going to apply it on each individual fiber in the composite in the direction of the fiber. And so then when we look at that failure indicator, we can see that we've got this X value here, which is going to correspond to the longitudinal strength of the composite. So the strength when the fiber takes most of the load and it's very strong and has this very high stress, low strain at failure. And then we're going to have this Y term here, which takes into account the strength of the material transverse to the direction of the fiber. So when that matrix is taking the most of the load and it's not as strong anymore and it's a lot more ductile. And then we have this S term here, which is going to be handling the shear components of the stress. And that's for this scenario where you have this shear loading happening and you have these complex failure mechanisms that are happening as a combination between the fiber and the matrix, like something like a fiber matrix debonding or a shear failure. So we're going to take this Sci-Hill 3D transverse isotropic criterion and apply that directly to the individual fibers using our first pseudo-grain failure method. So this is the damage model that we're going to be using then. So then how do we go about generating this damage model? Because as you can see, we've got 3 different parameters in here that we need to fill in. And obviously this is a relatively complex situation. I guess one thing I missed here that I want to come back and touch on is that when we run this type of model, we're going to end up with something like this, where basically we can vary that individual orientation and see a different SN curve for each individual orientation. So, this is a representation of that fact that the SN curve changes as a function of the loading and the fiber orientation. So looking at generating that composite damage model, so the input for this composite damage model, we're going to need some test data at a very simplified level that we can then apply to this damage model to predict these more complex loading scenarios. So in this case, the simplified data that we're going to need is we're going to injection mold a plate, and we're going to cut some dumbbells from that plate relative to the direction of flow. And I think they touched on this in the previous presentation as one methodology for testing these materials. And one thing that he said in that is that this was kind of a simple, when they were doing it, it was more of a simplified approach because they were assuming that all of the fibers are aligned in the direction of flow. But one of the really nice things about Digimat is that we're not just taking into account what's the mean direction of the fibers, we're taking into account how much randomness is in there and how does that change as you move through the thickness of this. So we're actually going to be looking at, what is the actual fiber orientation in this part and representing that pretty accurately. So we're gonna take these dumbbells that are cut from the plaque at these different orientations, and then we're gonna test them, and we're gonna end up with 3 SN curves that look something similar like this. So up at the top here, you have this 0-degree curve. It's obviously the most durable material since the fibers are mostly aligned in that direction of loading. And then down here at the bottom, you've got this 90-degree curve where the matrix is taking most of the load, and it's the least durable scenario. And then you have a bunch of other scenarios that can fall in between. So what we'll do is we'll take these 3 pieces of test data, we will bring them into Digimat, and from that, Digimat will then reverse engineer basically 3, you can think of them as ideal SN curves, which represent the parameters in this failure model here. So you see the X, the Y, and the S, and those are going to be represented here in the X, the Y, and the S. So we're going to reverse engineer those parameters for our damage model. We can then come in and we can change the loading, we can change the local fiber orientation, and we can use that to predict what our new set of SN curves are going to be. So an example of that you see here, you've got basically our 3 pieces of input data. We're going to bring those into our reverse engineering tool, and out of those we're going to be able to predict, all right, what's the maximum, the most durable scenario for this material given a fiber orientation and loading, and what's the least durable scenario for this material given a fiber orientation and loading. And then we can predict kind of any state in between there, like this here is like a 2D random state. So if you had a weld line, that's what that would look like. So once we've got our damage model, then we need to bring all of this take that and apply that at the part level. And we're going to use the same process that we did before to come up with our stress state. So we're going to take the information coming from our manufacturing simulation. We're going to bring that into our finite element analysis and use that linear elastic analysis to predict the stress state in our part. We're then going to use our SN curves to come up with our damage model. We're going to bring in those fiber orientations into nCode, as well as that stress state coming from our previous finite element analysis, and we're going to use that to do our part level lifetime prediction for our component. So we can look at how that might be applied. In this case, the application we're talking about is a relatively simple application. It's a great application, though, I think, for demonstrating this technology because it's not so complex that it's difficult to understand, but you can see it's got these varying rib features that are happening through here, and so that gives us some really interesting things where the fibers tend to align down the direction of those ribs, and then at these joints right here where you have basically two flow paths coming together, you get these little balls of randomly aligned fibers. So it's a relatively simple geometry, but we get some really interesting microscopic effects happening. So in this case, we're going to look at this beam made with a Tensile material. It's a PA6 nylon with 30% glass fibers. And we're going to put it on this 3-point beam bending test, and we're going to load it vertically. And basically, they're going to run that load they're going to run this setup for 3 different loads and then determine the fatigue life of the part. And we went back and then looked at each individual part to understand where did the cracks start and how did this fatigue failure initiate. And so what we see is that in most cases we have this fatigue failure happening right down here at the base of where these ribs connect at the center of the beam. And if you think about the microscopic effects that I was talking before, it makes a little bit of sense that we would see that here, right? Because we've got these fibers that are aligned very well in the direction of the ribs, and then at this joint here we have this little ball of randomly aligned fibers where the material is not going to be as strong. So you put a stiff part right next to a soft part, you're going to end up causing yourself some problems. So to start this whole process of doing this fatigue life prediction, we need to start with our input test data. So we're going to injection mold our plaques, cut our dumbbells, and then do our fatigue testing on those dumbbells. And so you can see the scatter of that data here. So up at the top, you've got the 0, the 45, and the 90. From there, we're going to bring all of this into our reverse engineering tool and come up with those parameters for our damage model. And you can see those represented here. And one way to think about this red and this black line are kind of your minimum and your maximum fatigue life for this given material. And then we can go ahead and use that model and reapply it to the microstructure that we're seeing inside of those individual dumbbells to see if can we predict these fatigue life of the dumbbells. And you see that for these, it's basically the same orientation state with 3 different loadings. We're able to get a very nice correlation there. So that gives us a good indication that we should see good correlation at the part level. So if we go ahead and look at our analysis here, one thing that's worth mentioning that maybe I should have mentioned earlier is, when we're looking at these materials, at least in this level, we're only looking at the tensile strength of the material. And that's really important when you talk about plastics or these composite materials because they tend to have a very different strength in tension versus compression. They tend to be a lot higher, a lot stronger in compression. So then when we move ourselves to our analysis, we're really going to focus, instead of looking at the compression side of the beam, we're really going to focus on the tensile side of the beam. So if we look at that tensile side of the beam after we bring that damage model into nCode along with our stress straight that we generated in our finite element analysis, we can then look at the fatigue life prediction that happens. You can see that it's highest right in that area where we see the beam failure actually happening. And then we can go ahead and plot those against the experimental results. And what we see is relatively good correlation within a decade or so for each of the 3 different cycles. We're definitely farthest out here at the highest loading cycle. And the question there becomes, we're starting to get down into the 10,000 cycle range. For these types of materials, is this still really high cycle fatigue, or are we starting to see some damage accumulation? So in conclusion, multi-scale material modeling, such as Digimet, allows us to accurately predict composite performances, such as fatigue. It allows us to enrich the classical CAE methodology with some key microstructural information, that really being the fiber orientations and how that affects the mechanical properties. And by accounting for the variable fiber orientation shaped by that manufacturing process, we can really predict the fatigue life of actual engineering components. And this is something that we've demonstrated not just in these simple lab-type test cases, but on real engineering components used in the automotive industry today. So before I finish up, I want to leave you with kind of one thing to think about, or maybe an interesting movie, I guess you could say. When we started talking about these materials, one of the things that I said right off the bat is that these materials are very highly nonlinear, and so that's why, at least initially, we're focusing on this high cycle fatigue. But for these materials, it's oftentimes a combination of low and high cycle fatigue. So in that case, we need to start looking at more complex material models, things that can take into account the viscous effects of that material. And so what you see here is an example of a finite element analysis where we're basically doing some low cycle fatigue loading. So if I go back there, you can see the load kind of gets applied and then taken away and applied and taken away. And what we want to know is, can we predict the damage happening in this high cycle fatigue? And so what you see here is the plastic strain in the composite material happening. And indeed, when we apply this viscous model, you're able to see that damage in the composite build nicely. So a little bit off topic, but just something interesting and to share and to kind of keep in your mind as you're dealing with these materials. So thank you so much for your attention.